Okay, I'm back. Sorry about that. I had a computer crash for some reason when I switched between the tabs. But let's continue. Uh, that was the first time that happened. Okay, so
Kind of a different feel from how most
and anyway, I found the second video I was started watching. That is about the uh, back propagation calculus. It's basically the math behind back propagation, which is required to understand properly to be able to write code for this.
introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3
By the way, okay,
biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the
uh, wait, it's did I just get spam in chat or is that just scam? Spam or scam?
activation of that last neuron with a superscript L indicating which layer it's in. So the activation of the previous neuron is a L-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with a constant Y, lets us compute the cost. And of course, AL-1 is influenced by its own weight and bias and such, but we're not going to focus on that right now. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this,
okay, so yeah, this is what we're trying to figure out basically. How is the result of the cost function affected by each and every set of weights and bias?
this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it. As well.
Wait, so how CL is affected by BL? And that one, wait, wrong order, times how AL is affected by CL. I guess this is the right order.
As well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is...
And then, okay, so CL is C0 is affected by AL, how AL is affected by ZL, how ZL is affected by VL. Yeah, I think
the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivatives. The derivative of C with respect to AL works out to be 2 times AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. With respect together idea.
So I did a math exercise on this a few weeks ago, where I think I might have some of this math written down in my answer. So I'm gonna check that out right away. Let's see. I think it's in my downloads folder. Probably not. Hold on, I'm gonna find this file on the other screen. Sign there. Here. Assignment 4 or 5, I believe. For this one. Okay. So I know I didn't take a lot of notes here, and I'm sorry about that. It might be unclear what is going on. This is probably what we are looking for. Yeah, it is. So L is the activation function, I think. And that one's based on the output, which is usually A. A is affected by the pre-activation function. The pre-activation function is affected by the weights. Let's bring up a paint document here. So basically, we're gonna call this one C, as that's the notion we're using. How is this affected by the weights? So So this should be, first we know that the result of the cost function affected by the result of the activation function. The result of the activation function is affected by the change of the pre-activation function, Z. And the pre-activation function is affected by the weights. We know, as I wrote here in the assignment, that Z, that's a basic calculation. Basically, Z is equal to weights T. So that's what do you call it when you flip a matrix? It's called transpose, I think. Yeah, it's a transpose. That is the word of the day. Okay, so weights transpose times actually dot product x, which is the input, can be written as a in many cases, but let's go with x now, plus the bias. And the activation function we are using is ReLO. ReLO is x if x is greater than 0 and 0 if x equals or is less than 0. I think. Let's double check this. So we have ReLO. Yeah. Okay. So we have this so far. And if we go back to the video, bring up Paint as well. Let's see. We're gonna frame this a bit. Oh, that was ugly. Let's just draw a box. Perfect. Okay. So that's what we know right now. And if we're gonna calculate the different derivatives, let's start with this. How C is affected by A. They use the superscripts here. We will skip those for the time being. So since it's multi-derivatives, or whether it's called multivariable derivatives, we have to do the delta, not just D. At least that's what I've been taught. So I go with that. And so they have the answer here. Not sure how they got there. Let's see. I see affected by A. That's a cost function. So the cost function is rather simple. It's what is it? It's the you know what? Let's turn on some background music. I need something to listen to. Okay, let's get back to it. So the cost function is, let's just check in the code. My brain is not braining right now. We used mean square error, I think. It's what's defined in static class here. Yeah, mean square error. Okay, so that should be then. What do we call those? True minus predicted. So y hat minus y squared. But they were using other annotations. So y here should be the, but that's input. Wait. Oh, hello by the way. Welcome to the stream where I'm suffering, struggling with backpropagation and math behind it. So take the predicted minus the correct label. What am I doing here? That's supposed to be... Wait. Oh my god. This is wrong. There should be an A there. There we go. And they claim that is the derivative. How did they draw that conclusion? So something's off here. C is A. A is true. Predicted. It's minus A. Ah. That's error. Mean square error. Why am I looking at mean square error here? Wait, should it be? Yeah, it should be. Of course. True minus predicted. I think. Let's look at the math I did a while back. So why? Okay, so predicted. That's the input. True one. Okay. So the input is A. So place this to the A. And that means, what does that mean? So here we have to apply the chain rule, right? So it's the outer derivative minus the inner derivative, isn't it? It's like a minus y times 1. Wait. Ah, damn, that's correct. So it's just 2a minus y. I'm sorry if you can't see this, if it's too small. Just let me know in the chat if it's impossible to read. I'm not sure what quality the stream is when it's live. Like, it might be lower resolution than the one I see. I'm having a hard time checking that. Okay, so second one is, well, let's frame this so we know it's done. Beautiful. Move a bit because it's like that. Perfect. Okay. We're looking at how the activation function's result is affected by the pre-activation function's result. And this can be written as this. Okay, so this isn't like proper math thing I'm going to do now, but I mean, it does give pretty good understanding for what I'm doing. And apparently the derivative ReLU is the step function. Why is it the step function? So look at a graph here. Okay, I have a graph. Can you hear me, by the way? Yeah, you can. Then it should move something like this. So it's 0 until it reaches 0. So if it's 0 or negative, it is 0. But then it can like increase as it wants to. And let's see. That means that, oh, I see what's going on here. So the reason the derivative is the step function is because it, after 0 and above, it changes by the x value. So that, like, the change is the value times 1. And at 0 and beneath 0, the change is 0. So this is just step of oops, I see the typo here. Don't worry. I saw it. Okay. Set. So that's just set there, which basically is 1 if z is greater than 0. And it's 0 otherwise. It's so hard to write with mouse. So hard. Let's keep this beautiful graph here. Just make it smaller. So we have this derivative now. Okay. Third derivative. This one's the easiest. So you've said W is following. Is the weight transpose times the input. Let's call the input x now plus a bias. And how do we find the derivative of this? Well, it's simple. It's basically just x, right? What? Yeah. Okay, so they keep using a as input here. I think we should use the same. So we're going to replace this x just an a. So let's multiply these together. Okay, that's we have 2 a minus y times a times, let's multiply that, times step z. Poof, like that. And I think that's it for now. Okay, this makes so much more sense the second time you do it. The first time I did this here, I barely understood anything at all. I just tried to do the math, had to do a bunch of Googling to remember how to find the derivative of stuff. And also, they had this this trick here. If you look here, if you can see the mouse, where is e to the power of negative z divided by some shit. This can be simplified to this, which was required to solve this exercise, but I couldn't see how to do that. But they knew. It's a trick, apparently. And I didn't know about this trick. But anyway, let's continue looking at the video. I'm just gonna pause the music first. Quickly reply to a message. Okay. So I'll pause the music now and resume the video. Are you ready? Okay.
And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples.
So here they're finding the average value, since they're using gradient descent and not stochastic gradient descent, which is the one we are using. So maybe we should change this later on to stochastic. to non-stochastic, just gradient descent, could be a good idea. But let's not do that now. Let's let's stick with what we got. We could add a comment in the code about that, because if this goes well, I would like to improve it. Let's add some text down here. Change from gradient, from stochastic gradient descent to normal gradient descent. The main difference is the introduction, batch size. Oh yeah, well, I'm trying to do this. Wait, CNN. Actually, this is not a CNN right now, just basic neural network. But the goal is to later on turn into a CNN as well, since just the basic NN is a good foundation for CNN. They are very similar. So I guess make sure to follow if you want to see me turn into a CNN instead. Okay, so I was just making a comment here. Oh yeah. Have you done anything like this before? Have you written a neural network from scratch, maybe? Or have you taken any relevant courses? Maybe you know how to use TensorFlow, PyTorch? Well, you should give it a try. It's super fun, and if maybe you don't know, Bob, it is way easier than it seems to use the libraries at least. And doing this from scratch isn't too complicated either if you understand the math, which is what I'm struggling with right now. Oh, data engineering. It's fancy. So are you working with that, or are you studying it? So like work or study, which is it now? Okay. So you're also a fellow student. Nice. Same here. So I've taken 2 AI courses so far, 2 introduction courses. The first one was very practical, like that we just learned how to apply it using TensorFlow and Keras. But the second course I'm taking now during summer, it's almost complete by the way, is more about the math, but just like an introduction to the math. So that's why I thought this would be a great project for stream, because now I have to force myself to properly understand all the steps, also more in depth, because math we have done so far is just like on the surface. We've just like looked at how to do the math but not properly done it thoroughly. Okay, yeah. A computer engineering student too. Yeah, cool. So I'm currently reading information communication technologies in Sweden, and that's it is like it is fun, but it's not super focused on the software, which is what I would prefer. This program also covers a lot of hardware. Um, so, but the basics or the foundation is full of calculus. Um, I would say that to write just to be able to apply AI using a library like TensorFlow or PyTorch doesn't require that you fully understand calculus, though it does help. Because if you don't understand calculus when you use those libraries, you might not understand what some of the functions really do. You can get around it, that's fine, but if you want to do something more complicated like this, writing it from scratch, then you need to understand calculus. So if you look at, for instance, here, this is a channel 3 Blue 1 Brown, great channel by the way. Here they cover some of the math. So if you basically understand what's going on here, understand how to calculate these derivatives and how summation work, then you're good to go. You can learn to understand how to do from scratch. Okay, so let's get back to it. I was just adding a note here. Yeah, it's pain. Yeah, so I would say that it's the back propagation that is the pain. Like just forward propagation is pretty, as it's called, it's pretty forward. It's self-explaining. But back propagation, it's a pain in the ass. So, have you taken any of the calculus courses? Any calculus at all? Ah, you did. Have you taken calculus for multivariable? And also, have you taken linear algebra? Right. I forgot to mention you also need linear algebra for AI because it's basically just a bunch of linear algebra that also requires multivariable. Some of it. Uh, no, it doesn't cover everything of it. Let me show you my beautiful book here. Hold on. Okay, so so far I've studied 2 years at my university, and I have taken, I think, 6 math courses. Oh yeah, uh, awesome. So computer vision is super fun. Uh, I have done some of that. Hold on, I'm gonna show you something here. Let's see. So for my first AI project, but for the first AI course I took, I want to make a finger tracking software that allowed you to also like draw keys on a paper and press them. I never really finished it, but I can show you what I managed to create in a few days. Let's see. Recordings. Test 2. Wait, I want to download this file. Wait. Can't it download? Okay. Whoa. I am losing the control of my computer here. Okay, so this is what I created. So it's basically a CNN made to just classify MNIST numbers and characters. So it's for the extended MNIST, which I used TensorFlow to create. And then I used OpenCV for the computer vision, which used regions of interest, which is sent to the CNN to classify. Okay, so basically just paper here, and let's say you want to add additional keys that you don't have on your keyboard for some reason. I don't know why. Then you can just you can just draw boxes for the keys and draw the characters inside. So what we see now is like the filtered feed. This is what's being sent to CNN. First, we see settings is a bit off. We adjust the settings. Okay, perfect. Then we have the 8 inside the box. And now we can detect. So you can see it. You have detected an 8 there. It's 99% sure it's an 8. And it can do this for the whole alphabet and the numbers. It didn't work perfectly because, like, trying to determine if it's a 0 or an O, it's basically impossible unless you start with like clustering, for instance. So let's say that you have the whole alphabet written out, and then it thinks that the O is 0. You can just do some simple math to think, well, everything around it is letters, so we know this is not, it's not a number, it is a letter, so it must be O. Anyway, so this is how far I got. It could classify the written letters, but it couldn't follow or track the fingers because I never really added that. To make this, that's a good question. I wrote a report on this. I think I mentioned it there, but let me check that for you. How much data it was? Okay, so the report I wrote was in Swedish. I'm sorry about that because the teacher we had in this course wanted to try to change the IT industry in Sweden to turn it into more like a Swedish industry, so that they want us to learn Swedish terms. That was really confusing because everything you find online is in English. Okay, hold on. I'm just gonna look for the data part. Okay. So we had in total 112,000 images. So this was actually, yeah, it was an extended MNIST. So if you Google that, find this page. So yeah, it's this. It's enough to get around. And also make sure to use the balanced one. So if you just use the basic, like the whole set, you get 814,000, which is way more. But if you want to train a model as well as possible, you want it to be balanced. So I just went with the balanced set instead. So anyway, for the book I was talking about, for the calculus I read, so it was 2 calculus courses, and this freaking book, I'm pretty sure you've seen it before, but it was it was a lot of information. Like, I kept this like as this is my trophy from those 2 courses, and I'm gonna keep this forever. It's a lot of pages. It was how many pages? Including the answers, it was wait, how many pages is this? I don't know. They don't even. Oh yeah, 1,000 pages, I guess. Worst part about it was carrying it around in the backpack. I could get the digital version of it, but it's not the same thing. I prefer to have the real book. I'll always buy the course books and then sell them forward when I'm done, but not with this one because it's special to me. Oh yeah, they are super dedicated. They are. So fun thing about this book, I think it was this book. It might have been another math book. No, it was this book. Uh, there were 2 authors for this book, I think. Yeah, it was. So you can tell by the questions and the explanations which author wrote it. Like they changed the structure of the sentences and also the type of problems. So it's like, oh, now it's the other person writing all of a sudden, or now it's this person. Well, that was fun. Okay, so I gotta write this down so don't forget it. So right now the model I'm trying to create uses stochastic gradient descent, but I'm gonna change later on to just normal gradient descent. And the difference there is that during the backpropagation, which is the training, it basically instead of adjusting after have looked through all the data, it will adjust after have looked just a few months of the data, like just a few. What do you say? Oh no, my head. Okay, let me start over. So, in stochastic gradient descent, we adjust after each row of the data. But in normal gradient descent, we do like batch sizes. So we predict a few values, then we adjust for the average. But this is something I'm going to do later on. Okay, so the difference is introduction batch size and average adjustments, I guess. We will scroll up and okay, wait, scroll up. Why do you want to scroll up? Right, I was looking at the math. So here just math. Oh, batch size. Sorry. So the batch size is basically a few data points. So let's say you have here, you have 10 rows of data, and you want to do backpropagation, then you would oh, bath. Oh yeah, sorry, that's a typo. Bath. Oh, bath, cool. Batch. Okay, thanks. Then I don't have to explain that. Perfect. Let's see. So I'm gonna have to resume this video now to understand this whole thing better. So bear with me. I hope you enjoy this channel because you're gonna have to stick with it for 5 more minutes. I'm sorry.
And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases.
Okay, I have to go back a bit.
And that we found
what I was talking about
over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this.
You're welcome. And if you want to check out what I did in my project, I can send you a link if you want to, if you want it. Let's see, because all the code is there. There you go. So the code and comments, it's all in English, of course. It's just the report that is in Swedish. And it's also, of course, it's all structured. So you have like one folder for the CNN. You have the program that you could see, the frame, and this also includes the computer vision that uses OpenCV. And hey, don't forget to follow. That's important.
This del z del w term for a del z del b.
Good luck.
And if you look at the relevant formula, that derivative comes out to be 1. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b.
Right. Okay, so we're gonna go here and we're gonna expand the math here a bit. So we know that, oops, wrong color. Here we have how the cost function is affected by the weight, and to find how it's affected by bias, it's very similar, like I said in the video. Basically, we can just copy this, paste it down there, remove the wait, set. What's going on here? That is supposed to be. Oh, okay. C is affected by W. Did everything backwards? I think I did the math backwards. I did. This one's supposed to be there. This one's supposed to be there. Wait. It gives the same result, but okay. So how W affects Z, how Z affects A, how A affects C. I guess it's just a matter of perspective. Let's remove this and copy it from above again, and we simply change W. Okay, and that will be B. So it says B, blah, blah, blah.
More than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b.
Yeah. Okay. So del c del b will be. Wait. Won't that just be 1? So del c del b is equal to del by del b. I know my handwriting is horrible, but sorry. Blah blah blah. So Z is B transpose times the input, which is A plus B. So basically, it's just 1. So this implies that del C by del B is equal to almost same. So 2 A minus Y times step of Z. Sorry, Z. Okay. Ah, by the way, thank you for the follow. Really appreciate it. Wait, why didn't I get an alert about it? Maybe I should add sound to the follow. I think I should. So before I continue the math here, I'm gonna adjust the alert box because I want sound. Okay. Settings. How do I change the alerts? Settings, body, blah blah blah. So if you can follow. Oh, here we go. I can select. I can choose from these. Oh my god, so many options. Spooky bell. Nope. Sorry, that's loud. That's loud. Okay, let's find another one.
Thank you. Thanks for the dono. Thanks for the follow.
At least was happy.
There we go.
These are horrible. Oh. I think this one is subtle enough. Oh my god. Oh, this one's nice. I think I'll go with that one. Okay, let's try it out. Oh, that's good. I like that. And why isn't the chat box working? I noticed that while I was chatting with I predict people, no chat messages were displayed. Why? Disable, show platform icon. Sure. Settings. I want you guys to be able to see the messages. Is anyone in chat who knows a lot about Streamlabs? Because I can't get it to show the messages for some reason. Streamlabs messages not showing in box, I guess. Chat button display chat space. Consider this. Check the log settings in Streamlabs chat bots. Oh, maybe I don't have a chat bot. Let me look into that. Chatbot, okay. No. How do I? Okay, chatbox, basics.
Add a chat box overlay to your.
I'm sorry, but you're gonna have to watch
In
this
this
with me.
video, I'm going to show you how to add a chat box overlay to your stream. A chat box essentially a chat box is a widget from Streamlabs designed to help you improve. Is a good move.
Yeah, we know what it is.
Chat layer. box overlay. Now, when it comes to adding a chat box overlay, all you have to do is visit streamlabs.com and download Streamlabs OBS. Open Streamlabs OBS and add a new source. Add a chat box widget, and now your viewers will see your chat box overlay on stream. Pretty easy, right? We try to make it as simple as possible for all of our Streamlabs OBS users, but what if you want to kick it up a notch and add a little bit of extra flair to your chat box? Visit streamlabs.com and log into the dashboard. Click on all widgets on the left-hand side of the dashboard. Then click on chat box from the widget gallery. Changing the look of your chat box by using show messages disables the messages in chat box from fading. Chat delay sets how long it takes for a message to appear in your chat box. Hide chatters hides common chatbots and or commands that start with exclamation point. Custom bad words allows you to add custom words that you do not want to appear in your chat box. You can also change the theme of your chat box by using stream overlays. The Streamlabs library has thousands of stream overlays with custom chat box overlays that match Streamlabs OBS. You have the option to install the chat box widget. Now click install, and now you will see the chat box theme OBS. Choose which widget you'd like to install. You have the option to install all of them or choose to install specific ones. For example, in this image here, we are only installing the chat box widget. Now click install, and now you will see the chat box theme from this overlay displayed on your live stream.
That did not work.
Now, if you don't stream with Streamlabs OBS, perhaps you just use regular OBS of Studio and
okay, that video did not help me a lot. To look at my settings, box, Twitch, old school, nah, chunky, no. Okay, let's go with that one. Still nothing. Okay, well, you know what? Let's screw this and just continue. Okay. So we have our extended math here, which is great.
And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight.
What it was talking about.
You can see how sensitive this cost function is to the propagating backwards comes in. You can see how sensitive this cost function is. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely,
okay, this is interesting. So, how sensitive the cost function is to activation in the previous layer.
This initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight, WL. And again, even...
Wait. What just happened?
Even though we're not going to be able to directly influence that previous layer activation.
So how Z. Okay.
It's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output.
So we have the cost here.
That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has...
So let's take the code here. Blah. The mean square error handles matrices. But this is, wait, something's off here, because since this handles matrices, it means it covers batches. So this is supposed to take in two matrices. If you look up where it's used, we use cost function. We just send it one value. This is wrong. So we're gonna have to create one more static function here. Static method. It's just gonna be called def squared error. Which is just, we're not gonna sum anything up. We're just gonna, we don't even need numpy here. We're gonna take the true value minus the predicted to the power 2. Okay. Just to make sure everything's working. Yes. Where is this being printed? So print error. We do the backward. Backward doesn't print anything there, so it prints from the layer. Yeah, loss gradient. These dot product. Even use just, you know what, let's actually fix this properly. We're gonna remove the squared error again. We're gonna stick with mean square error. We're gonna have to introduce batch sizes, I think. Let's cheat here. If we're using mean squared error, don't we need to apply batch sizes? Stupid question, but it will say yes, we need that. Yeah, exactly, we need batch sizes here. So it suggests that we take the batch size here as an additional argument, rather one more parameter here. And okay, so here, wait, range. What is the third over? So we know start at 0, go to the length, the batch size. Should this be negative -1? so. So these are the steps, I think. Yeah, supports index. Yeah, that's the step. Okay, start, stop, step. Perfect. So batch X, batch Y. This is correct. Yeah, we select the data points. We want to predict a whole array here. Predict. Okay, so for inputs in inputs, we will update the inputs. Wait, what? Input is not accessed. What do you mean? Hmm. We for each input we and for each layer update this input. And it's not. Oh, wait, what? Wait, if one do it for each. So pass the layers here. 4 layer and layers. Oh, there we go. Okay. Now we predict all of the given data points, and based on that, do the prediction. After the prediction, we'll do the backward propagation. I got to sit up properly. Okay. So about that. I think volume that should be fine. Okay, we do a prediction, bunch of predictions. After we want it cost, call it cost function. That means square error. That should be fine. If we comment this out, run this. Should get some errors. Oh yeah, right. We need the batch size. Let's say I don't know, 100. Okay. Operands cannot broadcast together with shapes. Okay, so I have 2 shapes here. Oh. Wait, mean square error is getting argument with that shape? That's not right. Predicted values. Predict. And predict. Look at each input row, right? now. Okay, to do all the predictions, but this makes no sense. Why are we turning this? Yeah, these are the input. That makes sense. Ah, Taktia. Set. Okay, we have inputs. Those are correctly formatted. Look for each layer we pass inputs, update the inputs. But this should shrink after a while. So print. So this gives us 10 rows. 10 rows. Broadcast together shapes, blah blah blah. Mean square error. Mean square error is accessed via cost function. But the prediction, something's wrong with the prediction function. It should return an array of this shape, not this one. Let's print out bread. New line. I don't know. Maybe we can. Blank line. I want blank line. Oh. What about that? No. You know what? Let's just be lazy. And squared error. Squared error is called this function. Why is it never printed out? Let's try this. Okay, we're getting some outputs now at least. Yeah, that is progress. So these are the values we wanted. Oh, these are the correct labels, the correct values we want to predict. And this one. It just returns the. Yeah, that's the. Wait. 1, 2, 3. now I'm lost. Oh, it is 4 values. 4 values, 4 values, 4 values. 2 values sounds about right. Um, 2 values. The this. That's one. Print. No, we can actually just this one. It's save here after the loops. Run all here. Yeah. We need to create a new array. Oh yeah, I see it. So since we have a matrix of size, let's say x times 4, we can't just start converting some of the rows to x times 2. We create a whole new array. Matrix, sorry. Matrix. So let's scroll to predict. Let's call it new inputs, and it will be a just empty numpy array, I guess. And we will be adding pending songs. Wait, this input each layer. Changes. Okay, the just changed somehow. I should probably insert it into a new array. We'll just turn the let's okay, so I have this x times 4 matrix, and after done the predictions, I want to be, let's say, a x times 4 array. So I somehow have to convert it. I was thinking about creating a new array here. Start off as empty, and then we just insert values we found. So for each layer, that means we're gonna have to change the size of the array multiple times. Welcome to the stream, by the way. I hope you enjoy watching me suffer with with this math. Maybe not this math. This logic. Okay, so take but just one size matrix. That's that one. That is a matrix. And I'm gonna have to assign. So let's move this there. So prepared a new array. And we are gonna hand the result to it, I guess. And when we have, we don't need to update the inputs. Instead, we type inputs equals new inputs. So what I'm trying to do here is the following. Bring up Paint, and I will show you my art skills. It's just some of the math, not important right now. I'm gonna expand this. Right, if you enjoy watching me suffer with this, I suggest that you follow. It's gonna be way more suffering than this. I was thinking about when I complete this, I might try to do the same thing in Elixir. And if you don't know what Elixir is, it's a functional programming language. It's pretty cool. It's super effective. Oh, and it's very useful for writing algorithms. Okay. Anyway, so we give it a. We start off with an input that is, let's say, 4 times 4. Dots. Beautiful. Just beautiful. So out of the first layer, this is going to turn into let's see, 2, 4. This correct? Yeah. Give it that 4, poof, poof, poof. One for each node, neuron. Each neuron, 2 values. Yeah. And this one will turn into 2, I think. Maybe. I did something. It's complaining. So it says array missing require argument object. Okay. But how do you create an empty array of no specific shape? Oh. Like that. That was easy. Run all the blocks again. See what happens. Wait, what? Numpy don't have a pen. Okay. Oh, this is clever. This is clever. Yeah, that's better. Okay, so we're just gonna create an empty array here. We'll just append to it, and here we just convert the new input array to an numpy array. Damn, Copilot, you deliver. Shapes 1, 2, and 4. 1 does not slide. Okay. Well, it's a step in the right direction, I think. I'm gonna move the chat a bit. Why can't I move the chat? Oh, it's locked. There we go. Well, 1, 2, 4, not line. Blah. Let's look at what's printed out here. So, did it fit? Probably not. Yeah, it's a dot product. Calculate instead. And well, not the shape. Let's print its shape. Wait, nothing? Seriously? Okay. All board is correct. I'll be right back. I got a phone call I gotta take here.
I can hear you thinking, man.
I am back. Okay, so don't worry. We were looking at an error we have here. So take the inputs and let's print input shape, inputs shape, and do that instead in that order. So we get 10 times 4, so 10 rows. That's a batch size. We then have 4 columns, 4 attributes, as expected. We send this into forward, and forward takes input argument. So I'm gonna print here inputs as singular shape. Input, not shape. Debug this. Debug the shit out of it. Okay, so this is shape. That's great. So we just grab each data point one by one. And we we take all 4 of them. I think we have to do one thing here. I always lose this function. I forget where it is. Diction function. Just to, yeah, sure. Just add some shit comments so I can see it next time, so I don't lose it all the time. Okay, so the input shape will be changing now and then, like after each wait. That's not right. Wait, is it? Yeah, it is right. I think. On all. Blah 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 blah. 1, 2, 3, 4. Wait, that's. Oh, should it change the size? 2, 3, 4. Shape. All those. Insert the first into the layer. And that we need to save input. That should be mutable. So we pass that input through all of them, but it's gonna change in size unless we make a copy of it. And when that is done, we will input new inputs and input. Start here. We look at the first data point, first row. Pass that into the first layer. Or two layers. Shape for yes. I think I'm gonna update this. I want to clarify what's going on here. Go. Sure. I think they'll have the alt shape. Yeah. So if we follow this, the information we get about the build model, we get that the model looks something like this. We have inputs. We have hidden layer. Then we have one more hidden layer, followed by an output layer. And these are connected like this, connected to each, every one of them. And pairing continues. So this is correct. This looks right. And wait, something's working all of a sudden. Okay. First input chip 4, chip 4 to 1. So if we some of the components, all this printing, right, is here. just hide those for now. Batch wise, we'll pick that. Wait, this is odd. So we only get one prediction here. Batch let's call them real. Red. That has some space in there. There should be more than one. Ship prediction. Thread. Inputs. Layer. Wait, I'm messing this up now. Yeah, this is wrong. Because now we look at each row for new inputs. We basically shorten it down. Okay. Outside new array. Oh, my head is not working. Okay. Read inputs. Row. One of these. Create new inputs. Something like that. Just add it and we assign. So that's obviously wrong. So what we need to do is just do input. Wait. Oh, wrong language. I think I wrote JavaScript, TypeScript last time I coded. Now we'll get an error. Yep. So we take the input. Take one that. I pass all the layers. It's going to change size. And when it's done, we add it to the new array. There we go. Oops. Maybe we can flatten this down to a one-dimensional array. Now looks weird if we don't have to, but it would be nice. So can we flatten this out? let's be lazy again. How can we convert this? Is it map? I think it's mapping. Unless it's something built into NumPy. Yeah, it's flattened. Cool. Wait, print. Yeah, okay. See if that works. That did work. Perfect. So now we know that's working. The predictions are correct. Is the back propagation correct though? Let's count this out. I'm gonna run all again. I don't see the error shrinking. Let's all print out the error in some cases. If 300? Nah, error 10. So this does is we use modulo 10, meaning that let's say we have let's see 9 modulo 10, that would be 9. Another example would be 10 modulo 10 would be 0. So it's like that we restart counting. If we have 11 modulo 10, we would have 1. This would make it a bit clearer for us. So you see that the error is it's not really changing. So we know that the back propagation is not running as it should. Okay, we know that much. It's something. Let's go back to our video and close down some shit. Oh, maybe we want to keep that one. Oh, too late. I will pause the music a while so we can focus on this. Focus on this together. Oh wow! Damn! So I'm looking at a picture of something my brother's building. It's an outdoor kitchen. It's looking very good. Wow. It's good. Wow. Okay, so we were just about pausing the music and continue watching this video.
It has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight mate over ALJ minus Y. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output.
Right. Before we continue this, I remembered we started applying the gradient descent algorithm, so we have stepped away from stochastic gradient descent, which means we can remove this. Okay.
You take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like Z, so that the activation of the last layer is just your special function, like the sigmoid, applied to Z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the 1 neuron per layer case, it's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is,
Here. So how it is affected at a certain activation function. L-1, that would be just before.
on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up.
Okay.
And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you can just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation, the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it all.
Okay. I'm not ready for this. So, let's look at the math we have here. So, we know how C is affected by the weight, by the bias, and how do we decide how to adjust it? So, Copilot suggested this code to the left here. We calculate the gradient of the weight and bias. The gradient of the weight is dot product of the loss gradient. But gradient of the weight is dot product of the loss gradient and the inputs. Okay. And the gradient of the bias is the loss gradient. Okay. Then we update the weights and bias using the gradients. Return the dot gradient for the next layer. We we should double check that we actually keep the inputs here. Just to make sure. Print self.inputs. We probably do, because otherwise it would be a runtime error, I think. Wait, there's nothing here. What? Backward. Inputs, I guess. Solve.inputs. Let's try that, see what happens. So start with all the calculations. We could hide. Wait, why? Let's just batch size. Yeah, we do all the whole data set. What is it? Number two. Number two is epochs. Okay, let's comp this out for now. Maybe we should. Epochs. That's wait. I. Yeah, you know what? Let's ignore that for now. Do you get any output at all? No, we do not. Okay. Oh crap! You forgot this. No. Ha ha. Shapes 10, 2, not line. Blah 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 blah. Okay. 2. That's dot product. So we get the inputs. Yeah, we have the inputs it received. Then we have something else. Where do we print that? Print that here. Backward. What do you want to pass for the late? Sure, sure. These are the ones. We have the loss gradient, which is this. That transpose is basically the same when printed out. So printing out the transpose is unnecessary. But those are different shapes. The loss gradient it receives is okay. Where do we call backward? We call backward. Yeah, we'll call from here. Oh, from here. Oh, okay. Loss gradient. This isn't the loss gradient. Is it? Wait, do you? Am I making a mistake here? So the loss gradient should be. So the loss is mean squared error. look at the backward 100 blah. I think I misunderstood something here with the logic. Let's see if I have cheat sheets or something. I do not apparently. Anyone in chat have an idea how to go about this? Please let me know. So here, basically find the difference. Loss gradients. Gradient descent. Loss. There we go. Our loss function defined in part 1 is. Yeah. So here we use mean square value, mean square error. Yeah, these are the components of it. Yes. Gradient descent with respect to weights. So our last function by part 1 is this. Immediately identify this as composition functions, which is the chain rule. Find our equals as. Okay. Let's compute the gradient with respect to weights first. We have hmm. Oh crap, I gotta eat lunch. Hold on. Just gotta put my food in the microwave. Oh, never mind. The oven. I don't have a microwave. It's a luxury I cannot afford. Crap. There we go. Okay. So lunch in 20 minutes. I guess it's time for that one. Yep. So who were we? Trying to figure out how. So that's the error. That's not a. Would you suggest? But wait, does this make sense? Maybe loss gradient. True, my prediction. Let's draw a few lines here. We are say that we guessed that value. Wait. The guess was this. The right answer was this. Let's say 50, 100. Suggests true minus predicted. So it will be minus 50. Yeah. Okay, so this is then minus 50, so that we get from 100 to 50. That's the difference we want. And so we know that. We know like the error we have there. Pass this to okay, each layer. We update the loss gradient because we wanna we want to need to change it because the loss gradient changes after each layer. So for the first layer, basically for the first layer from the output from like the reversed order. Here. Oops. Go. So we have the gradients here. We have the error that occurred here. So at the first layer, it will be here, the output layer. We will look. We tell you, well, this is the error, and you can adjust to this. And to do this, go here, look at the loss gradient, and that's this gradient. And now we need to adjust it somehow. So it suggests, so we know that this one is one-dimensional. Loss gradient is one-dimensional since this value is. And it wants us to take this dot with dot product to the inputs, but the input is 2. This is where things get fucked up. Really fucked up. So if we look at the math we did up here, this is weight gradient. Wait, here we have it. So that's the input minus y, which is the correct value, times a input times step function. This is how it changed. So what if we the problem here is that the a and y does not have the same dimension. Maybe that's fine. So minus loss gradient. This times the self dot inputs times the stepper function. So we need the stepper function. Let's wait. Is the stepper function built in? Insert stepper function. The argument. Self. Dot. To set would be. Seriously? It's just set? I gotta double check this, hold on. I guess it is. You know, to save some computational power, we will store calculate set here. We can reuse that. That should be the weight gradient, I think. Bias gradient, similar. It's not times that. Just remove that. Yeah. Wait, no. We just remove the A, which is the input. This should be removed. And now that we've done this, it might work, it might not work, it will probably not work. It did not work. Wow. Okay, calculate set is not defined. Well, that's not an issue. There we go. Okay, watch this crash. Yeah, it crashed. Operand cannot be broken together with shape 2 and 10. Yeah. It's a lot. It's a lot to learn on stream. Suffering, real. Yeah. Okay. This was online. Weight gradient. Here. Okay, so we try to multiply that. Multiply by said. That's basically a dot product, isn't it? Together shape 2 and 10. Oh, input is. So this was the input. And second value, and third value, I'm not sure what they are because I don't print it out. Loss gradient. Oops. Here we have some shit. It's being passed loss gradient. Why is the loss gradient so vague? So it's a first run. But the loss gradient is an array. Sounds strange. Aren't we used to take like the average value here? I think we're supposed to do that. Move this out here. And I guess we'll use error. Self backward. There's a loss gradient. So that's what we want to adjust. The loss gradient. That's the cost function. Cost and loss. Oh my god, what's cost and loss? It's the same shit. Okay, so we can just pass this one forward then, I guess. Let's just call it cost instead. Or loss. Comment it out. Sure. Local block print. What? Oh. Input is 0, 0. 0. What? Ah. Okay, there we go. That's better. So I had to that one. Okay, so these two inputs we're looking at here are the following. This line, this line. It's cross these two. And we have a loss here. I need to blah blah blah, self-biased learning rate times bias gradient. And some shape here is wrong. Is the bias one-dimensional? The bias should be two-dimensional. Let's check this. We can double check the bias here. Oh, welcome to the stream, by the way. I'm currently struggling with backpropagation. trying to understand like how it works from the core of it, not just how to apply it. So I'm trying to figure out the code on my own, basically, and just look at the math. So if you enjoy watching people struggle with code, then make sure to follow. Okay, so turns out the shape of this bias might be a bit off. Bias shape, delta bias shape. Wait. There we go. Okay, let's see. Go down. Right. Oh, bias shape is 1. Wait a minute. That's wrong. So this neuron, the red one, it should have. Let's see, we have 2 there. Both the weights it has. Let's call it oh, what should we call it? Look at the model. We have 2 hidden layers, yeah? So 1, 2, call it 3. And those should be. Wait, how would it be placed? Columns? Or it's rows. So we have the inputs. Let's call it A. So A1, A2, I guess. This is superscript, so this is not to the power of. This is not cubed. This is not squared. B 3 should be 2-dimensional. So basically, A superscript 3 is equal to B superscript 3 transposed times A superscript 2 plus B superscript 3. Thus B should be 2 values, but right now it's just 1. That's wrong. Damn, that's not good. And so we'll have it. Oh, wait, what is that? I gotta think. Yeah. Let's go look at where we assign the biases. We assign the biases when we call the function get set input shape, I think. And self set input shape is defined under here. It's amount of neurons. That's not correct. That should be same as the input shape. I think. I'll probably destroy something else. I did. So anyway, I'm gonna have to grab grab my lunch now. But I think I might be watching videos at the same time, some videos about this actually. Application, neural network. Let's see if you can find a good video on this. PyTorch, no. You might have something.
Hi everyone, what you want to do is I'm gonna see afterward. This is where much of the computation is done, and here I'm saying it's an output. This is what we're doing here. So fit. Well, it does. It's the for the at this index for this particular neuron. So by doing this, we're gonna get the correct weight. We're gonna multiply by this neuron delta, and then we're gonna be able to sum them.
I don't think this video is great, but let's give it a try. I'm just gonna go fetch my lunch.
Hi everyone.
So I'm back. I'm gonna, as I said, eat some lunch and watch this video. So feel free to stay with me and enjoy it. At least I hope you can enjoy it. I have no idea. It doesn't look amazing, but maybe it is. We'll see.
Today we'll build on last week's tutorial a code, the backpropagation algorithm from scratch in Python. If you want to get a refresher on the theory, to go take a look at my previous video, and let's jump right into the code. So here we are in this notebook. We don't only have the backpropagation algorithm, we have the multi-layer perceptron, which we need some kind of network to do the backpropagation. So it's breaking down to like two parts. We have the neuron, and then we have the multi-layer perceptron class. However, it's not very flexible. The goal was just to showcase the backpropagation, how to code it. So here we're going to use a two-layer perceptron just for demo purposes, and we're going to try to learn the XOR function, and we're going to use the delta technique for the backpropagation implementation. So in the description I've linked a very good tutorial for the derivation of what we're going to be using. So take a look at this. So let's start. We're going to start from the bottom. So here we are. So we're going to do the XOR function. So it's just like 4 inputs, and those are or y's. So it's one or the other, but not both. So 0, 1, 1, 0 work. We're going to use two layer, one hidden and one output. So the output will only have one neuron, and then the hidden layer can have a varying number of neuron going to start with 3, and this is the number of iteration. So let's test the full thing. Here we're creating the classifier like we'll be in scikit-learn, and then we're fitting it, and then we're checking if the error is going down. Oops. Yeah, I have to run this. Okay, so with that much iteration, we still have like half. We have a random classifier, so if we increase it, we still have this. Increase it again, it's going down, right? It's going down, and then we get no error at some point. So after this much iteration, we have low amount of error. However, if we increase the number of neuron here, so we make it a bit wider, it's a bit more dynamic, and I think we get there faster. Or the training is a bit slower. Usually, what you want to do is have like a deeper network than a wider one. But for demo purposes, we can see that it's keep it at 10. It's working fine. So this is what we're doing. We're creating this class. We give the number of neuron that we want in the hidden layer and number of iteration we want, and then we just create this classifier, and then we fit it with our data. And this is where the backpropagation is. So let's look at the multi-layer perceptron class. It's right there. It's a bit verbose, but so there are some optimization to do, but here it's more about documentation than optimization. So if you want to take a look at this, it's on my GitHub, which is linked in the description. So here, this is the constructor. So we have those parameters, the learning rate. I'm not changing it in the testing, but you can just set it if you want to. Here I'm constructing my layers, and here I'm just setting some parameters. But here I'm constructing them outside in. So I start with the output layer over here. This is the neuron class that we're going to see afterward. This is where much of the computation is done, and here I'm saying it's an output neuron because that will change how we're doing the backpropagation. And here I'm creating the hidden layer, and if you look here, I'm attaching this neuron to the other layer that was there previously. If we want to have multiple layers, this will be a bit difficult to do, but this was not the purpose for this particular video. And here I'm attaching this neuron over here because we need some kind of relationship between the two layers, and over here I'm just like saving this neuron over here. That's it for the constructor. If we look at, we're going to look at the predict first because it's an easier one. What we're doing over here is we're gathering all the activation. So it's the forward pass. I have a video on this if you want to have a bit more information about the theory. But the idea is that here I add the bias value, and then I just go through each of my neuron, and I do the activation, and I just get all of these activation. Those will be my feature for my output neuron, and here I'm just adding a bias again, and I put that into my output neuron, and I use predict for the output neuron over here, right? So all the neurons here, all the perceptron, the neurons are using predict on some data. Here it's the row over there, and then after I go through this activation, and then this activation go through this other neuron activation, I look at if the activation is greater or equal than 0.5. If it is, it's a 1, otherwise it's a 0. But that's pretty much it for the predict. And then the fit, this is where most of the meat is. So here I'm not using NumPy, I'm just using some bunch of lists, so it's not that optimized, but it doesn't really matter. So here what I'm doing, I'm initting the weight on each of the neuron in my perceptron, including the output neuron, right? And we need to do that so that here it like how I've done it is you first create your architecture and then you create the connection when you're ready for the fitting. So this is what we're doing here. So we're creating the connection over there, right? So this is all creating the connections. Here this is where we're actually training stuff, and that's it. So if we look, we're gonna do this training regimen number of iteration time. So in this case it's a lot of times, so that's what we're going to do, and we're going to use stochastic gradient descent. So at every time what we're going to do is we're going to take a random integer, right, from 0 to a number of row, and then we're going to select a row. We select that row, we predict what this will do, right? So for giving that row what is our prediction, and then we're going to compare this to the target. So this is stochastic gradient descent, where in the gradient descent algorithm is not implemented over there, but this is how I select the row for my stuff. The stochastic gradient descent will be used over there in the calculate update. So perfect, that's it. So here we calculate how we should update all layers. So we start from outside in, so we start with the output layer, so just one neuron here. We calculate the update given the learning rate and the target, so stochastic gradient descent will happen here, and then we do the same thing for
this is what I'm looking for. This is where I'm kind of stuck right now. Yeah. Sorry. So we look at the model, the output neuron, calculate update. Self the learning rate as an argument target. Okay. So for neuron, self perceptron, calculate update. Okay.
the hidden neuron layer. We have to do them in this order because these guys are looking at the delta of these guys, and this guy doesn't need the delta of anything because it's at the end, but this is the order we need to do it. And once we calculate the new weights for all of the layers, this is where we update all of the layers. So it's like a two-step process. First you calculate what the new weight should be, and then you update them. If you don't do that, it will be messed up. And this is just to print at every iteration. So here the problem is with the implementation is that we're using the same data for training and validation. However, here it doesn't matter because the problem is fully deterministic. The XOR function is just there. You cannot just get more data. We've seen all of the problem, right? So there's only 4 possible states, and here we're just trying to overfit. Well, it's not even overfitting. We're just trying to fit this neural network to that particular function. So we're creating a black box that will do this function. That's it. So the 2 things that we need to keep in mind is calculate update and update. That's pretty much it. So this is what we need to check in the neuron class. So this one is the most verbose, right? And this is where I decided to put much of the computation, but we don't necessarily have to do that. We can do it a different way. But here I think I find it cleaner to do it this way. So this is the constructor. So we need to say what the position of the layer is when we create it, and if it's an output neuron. Here we need to do that for getting the right weights in the next layer. So in the hidden layer when we get to the output layer. So here this is just for some variable used to make it work, right? Here this is for the backpropagation. So we need the updated weight, so the temporary weight until we actually update. So here we just get if this is an output neuron or not. That will change the backpropagation. Here the delta, we need it to store it, and here the position layer also we need to store it. So this is needed because if the output, let's say the output layer is updated, right? We have the updated weight over here. The hidden layer will need that delta. Good. So here this function is attached to output. It's just to attach this neuron to another neuron. I said attached to output because we only have two layers and it's only the hidden layer that will actually do this. This is just a sigmoid, so this is the activation function we're using. If we're not using this one, then my thing is a bit hard coded to work with the sigmoid. So I have the derivative of the sigmoid buried down there. But if you want to have any kind of activation, we're gonna have to look more about something called a computational graph and automatic differentiation, but this is not what we're doing here. This is when we init the weight, so we just init them randomly, right? Yeah, that's pretty much it for that. And over here, this is the predict, right? So it's basically the same thing as before, and what we're doing here is we're just summing stuff, and we're doing activation plus the weight times the feature. That's all we're doing here. Here, if you see, I'm saving the inputs as we need them for the backpropagation. So we predict, this is the forward pass, and we return the output, and this is where we actually update. Wait, this is not where we update. Wait, here. This is where we calculate the update. So remember, we calculate the update and then we update. So the backpropagation stuff is mostly here, right? And the backpropagation, how it works is that there's this thing called the delta, right? And it's used to calculate the gradient. So once you have the delta, you do this times the current input and you give you the gradient. So how much you should move. And this is where you can actually use gradient descent, right? And it's stochastic gradient descent because of how we sample the row in the dataset.
I don't feel like this helped a lot. What do people say about this? Kernel update, simple days, a great video. Some dislikes, is good or bad. Yeah, like okay. So the uploader claims this is correct statistics, but hi, yeah, hi. Okay. Let's turn the music back on. Blah. Okay, so weights and inputs. Yeah, right. So we changed the amount of bias they all have. We have to do that. Do we? Let's go there. Right. That's not the right place. Self calculate set. That should be up here. Yeah, here. I'll create this model here. Let's try to get some info out of it. Device is 2. Input shape is 2. That's correct. Wait, is the bias added to the output or the input? No, like, is it added to bias? gives one bias if the output is 1. Um, weird. Add all the weights together. Then we add the bias. Activation function. So yeah, the bias should be the same dimension as the amount of neurons. Bias vectors, different values per neutron. Okay. That means one bias value per neutron. What? Each bias value is unique to the neuron, which means the change I just did was wrong. This should be self.neurons. And now go to this. fine. We get that one is shape 1, that's the learning rate. Let's match the broadcast shape to 1. Wait, can't we just... What? Print. Earning rate. What that gives us. Yeah, why can't we do this? Non-broadcastable output operand with shape 1 doesn't match broadcast shape. What? What? Oh, okay. We are looking for. So, my guess is this shape is not the same shape as this. Let's explore that. Yeah, they are not the same shape. Because bias gradient is 2 values here. How can be 2 values all of a sudden? That's odd. Off there. Let's see. Okay, so something is wrong here. So we know that we get 2 inputs. Noise and loss gradient. Like I said, is just an integer. So the amount of inputs is what's causing this. But if I have 2 inputs, let's ask this one. Paraneuron. Okay, crap. I won't do this. Bias. Get 2. That's not right. This is wrong. So know how to change that. Oops. Did it calculate? Bring up the math again. Have it. But that's 2 values. Integer, 2 values. So we get said inputs that they are very similar, but we would need to flatten this somehow. Divide by 2? No. We can. What can we do here? This is a problem. Let's see if I have an exercise. For this assignment 5, perhaps. What's about clustering? This is not a clustering problem. Let's go to this file. Okay, I might have something here. Hopefully. Okay. Here just do some basic calculations. Yeah, as you can see here, we have 3 biases, so 1 for each neuron. Calculate the outputs, complete propagation. Hello, by the way, welcome. I'm currently working with back propagation and having a hard time getting that to work. Though it's super fun, so I hope you stay a while. Anyway, we do this basic calculation here. Blah 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 blah. So this isn't what we were looking for. Let's see what we can find here then. So here we just find how the relation between the loss function and the weight. So this is also wrong. Damn, there's nothing on it here. I will show you the problem, by the way. You just entered the stream. So we have a bias shape of the last neuron. This one. And the bias gradient shape we get is 2. Why is it 2? Wait. I might understand. I might know. It is. I think we are looking at the ones with these 2, which means we must go to where would we go? Here. So that's just a loss gradient you want now. So this should be past the one above. Sure. Bias gradient. I think so. Probably. So we'll pass these on. Oh, I this is probably wrong, but let's see. What the fuck? Was gradient shape 2? How? Eh. There we go. Okay, so it's empty. Well, let's just print out these instead. See what we get. Okay, yeah, that looks about right. Return of a dot product, so weights times price gradient. What? Wait, so weights, we have just 2 weights. And that price gradient. Um, let's go to the row with this error occurs. There we have it. 1, 2, something wrong with the dimensions here. So maybe weights. That wait should be other way around. Print some weights. Print from this. Scroll down. Okay. Yeah. Why does it turn out it's out? Self weights there. Old self weights. Old self weights is also the same. Why is it more like that? It's very odd. Yeah, this is wrong. I think. Wait, is it? Probably. Where do you assign the weights? Shape. a problem. For each of them, that means also for the bias, it will be the same though. Just scratch something else. Well, it doesn't have a channel. There's an error. So the weights. Let's put like that. Just to identify this place. Banana. Perfect. Banana. Yeah, right. Yeah, so we need to have it multidimensional. Okay. It is for each neuron. Meaning this moved. And this cannot be with that. Let's go to wait, no, the error is here. We're trying to make do dot product. Yeah. Trying to do dot product between these. What if we expand this? Change it the same dimension. It is to be the same dimension as this one. Let's just pull around here and go. See if we can increase this. Okay, so we're gonna create a code block down here. It's called test MP array. Perfect. And if we print this out, get that. If we type NP array test like that, we get that. Okay. Can we just like nest this somehow? Ugh. That we type, let's say 2 and 4. Okay, so we need to use this with this dot product, and it's called dots, and the dot product. Oh my god, I can't talk anymore. My brain is not braining. Okay, so these are they are the weights, and we're gonna take the gradient here. Just make something up. Let's call it 1, 2. Perfect. And let's print that out. Okay. So if I now create numpy dot and we take test and we take dot, it will work. This worked. Okay. Let's see the shapes of these two. 1, 2. Oh! It's not the same shape. It's because it's transposed. Maybe we shouldn't transpose it. But that would be weird not to do. Could it be that I might assign the weights in the wrong manner? I might be doing that. Yes, weird indeed. It's super weird. Har du det på jobbet? Har du det bra? Um, so we will. Where will we go? I think I'm gonna have to rethink this. Okay, so we take. Let's look at the math again. So actually, I have a great PDF for this. Let's see where it is. Not assignments. We're gonna go to that page. Go to lecture neural networks, part 1. I fear I might have messed up with the rows and columns, the weights. I might have mixed them up a bit. Okay, let's see. So weights. 1 row. Beep. Wait. This will tip, yeah. So this transpose will be like a horizontal matrix here, or array in this case. Then yes, that works like that. That means each weight is for each row is for one node. I would take that one, poof, like that. But okay. Make a NP array. Array. Let's see if Copilot knows how to do this tile. Oh! Okay, so let's try the tile function here. Shape of that's probably wrong. Okay. Four, 0. Flip them. Why not? Why doesn't that work? I need to hide some of this because it's too much printing now. Yeah, that's not right. Das is wrong. Das is wrong. Take the weight. This shape. Okay. but that's how so suddenly we have a matrix of this shape. Oops. And that's not what we want. Yeah, don't ask me what I'm doing now because I'm lost again. Step back. Okay. This value error. Uh, okay. So I get this. Start with one row, we transpose it, so we have one column. Wait. Column? So I think I have to flip it when I assign the weight. So that's the first one. I think so. It has to be the other way around. So let's say we look at the first layer. There's no weights of the first layer since that's the input layer. Second one is that. Third one. So this one should be transposed. Let's go to because let's double check this. These are like rows. These aren't columns. Okay, well, when we do the dot product, now I think about it, I think there's a mistake in calculate Z. Calculate Z, yeah, here, because these should be transposed. And when we add them, they should be transposed as well. Maybe we can just... what? Oh, you can just flip them? Seriously? Yeah, you can. Okay, cool. So I just noticed that I had done a mistake. I added the weights in basically the reverse order. The rows were the columns, and I figured that out by remembering that I never added the transpose to the calculation of this Z, of the pre-activation function. And because I did both of the mistakes, it worked. Like I reversed it twice, but when I was working on the back propagation, it didn't work because of, well, because of this. But I'm pretty sure I broke something else now. I probably did. Let's see. Self-weight, learning rates, blah blah blah. Okay. At least it's during the back propagation. Let's wait with it back here and see if we can just print out the error here. So it's for every 10th epoch, and wait. Yeah. Okay. Let's go. Should we know? We're gonna put out just red. Sure. Let's do that. Why not? And we get a bunch of values. Okay. That is good, but what do we get? I wonder what I broke now. So upon prediction, it's predict all of them, and what do we do? We will. I think we should get results here. Let's explore the model again. So we have our weights. Alright, so we got print. We want to print out both of them. Okay. We get weights, we have biases. And look at the second one. We know we have 2 neurons, so we should have 2 biases. Each neuron has 4, which is correct. If we print out model.predict, let's just give it a bunch of zeros. Okay. We change that to 1, 2, 3, 4. Okay, we got a different result. That's good. Then I wonder, in the prediction, why do we get wait, these are not the same. These are different. Okay, everything's working. Never mind, never mind. I was just being stupid. Run everything again. I'm gonna search for this row. Copy the error there, so we know what we're looking at. Okay, so weights, weight gradient, non-broadcastable output operand with shape 2-1, this match operand shape 2-2. Are we looking at it first? Here now. Not sure we were working right now. Let's add some. So we do a yeah. What do we do? The old weights. Without the weight gradient. Run that. Okay, so it's during the first run, which means we're looking at an error occurring here. We have that shape, so it is a vertical, just one column. So that makes sense. It doesn't work. Weight gradient 1. That means the dot product with complication here. Should this be transposed? No, it should have the same shape. Of inputs. Wait, we're looking here, by the way. This is what's interesting. Let's add a yellow dot there so you know where I'm. So we know that the A is inputs, loss gradient is in this case an integer. And this means it will have the same shape as the inputs it was given. The inputs given to it. Shape as inputs. Makes sense. So the weight gradient will have the same shape as the inputs. But the inputs should be exposed. This one's flipping. Flipping everything. So we take this patch as we send to predict. Input. No, the input should be just one line. The weight should be vertical. We can do dot product on them. That so the input input should be of that shape. The shape we got here. That is correct. Wait, and the weights should not be transposed. Oh my god. Okay. Look, just two of them. We have two matrices. They are both horizontal. We have the weights that they have to be transposed. We can do the dot product. So the error is elsewhere. We will restore this. We will go so these are the weights. The first same. The first neuron. They will be poof. Turn like that. So we have two rows, we transpose, poof, we have two columns. Which is 2 times 4, so 2 columns, 4 rows. Or if you say it the other way around, I don't know. We can... Yeah, what can we do? Get this error on that line. But they should still be transposed. Wait. The first run works fine. We flip them and we toss them in there. Second one is not identical. Why is it 4? This is... I have an idea. On the layer, def get identity. Identity. Self. Turn. Self name. Self input shape. Get blah blah blah. Okay, we can use this to verify what's going on. We will... That's not working anymore. Right, where to call it? Yeah, let's remove that logic to the layer abstract. Now we can go to calculate set. Or print this dot get identity. Self dot get identity. Scroll down. We look here. Layer 2. Wait, that's the first layer. Yeah. That's great, I guess. Output shape is 2. Output 4. Wait. It's 2. That is the weights. They all get 4 inputs. So each has 4. Poof, poof. Did it operate on that? This transposed. Flip it. bits. Let's say have three. Oh, let's say we have two. Or three, yeah, three. Three is fine. 4 inputs. It's transposed. It's more like that. It's one column per wait, so this transpose up there. Unless I see those as columns. Means we have another error. Okay, so this worked. Let's move the printing from the calculation of Z. Go back to the error at hand. This one. 2122. No, that's the error. So we know that the input is this. So our input is 1. Let's call them A1, A2. A1, A2, we have our weights. 1, weight 2. So as soon as we see the problem, we can't do dot product on this if we transpose this. This will not work. So you wait this. Something is off here. Yeah. Because this will give us when there's the same shape as the input. That means the input has to be if the input is like that, and the weight is like that, then it works. But this would be transposed and it would work fine. Should not be more like that. It's required that we change the structure of the. If we um, where does it go wrong? We have this. We have the weights. And the weights are already 2 rows. Should they be though? They should be. Wait. They're laying down. Standing. Both. You take for granted that they're it's not laying down, it's standing up. Oh my god. Okay, so this is a problem. I have been writing codes like this was like horizontal. It's gonna be vertical. It's gonna be standing up. So the input has to be transposed for this logic to work. Oh, for this, if I'm gonna follow the math correctly, then we have to flip them a bit. So let's go to the inputs. We send it in here. Prediction, no. Oops. Can't just keep flipping it. So maybe we have to think backwards now. Maybe that's what we had to do. So we can keep it like that, which means we generate this one flat. This. That won't do. This one has to be tilted. Well, count. Maybe we can just transpose it there. new shape. Some work. Doesn't work. Why does it work? Uh, okay, so if it's one dimensional, we can't just flip it. No. So it's not possible. Unless there's a list. What? What do you mean it's a list? Okay. Well, that's a list. Let's look at this. Hold on. Let's see. Where was I? So right now, generate like this. So for the second layer, this layer here, generate the weights like not like that, but standing up. So like this. Then we have a inputs. So get 4 inputs. This won't work until we transpose this. And when we transpose this, wait, right. So generally like that. Do I have to think of everything backwards? Oops. And maybe it does work. So column for rows, meaning that is our input. And want to generate these weights. Look at second layer. This one. 2. That's great then. If we assume this is how we generate columns for rows. Perfect. then, this structure we have. Go to this row. We're gonna copy that, bring it with us. Yes. And this. Okay, so I see the problem. So the this DCTV del or what you call delta del C del V, it will have the same shape as the input. And that just doesn't work. Does it? It will not work. No, it will not. Look at this. But no matter what to do, have the wrong shape. So the input is of this shape. The weight is of this shape. So first one is columns, meaning values we have now is the following. The inputs will be 0, 1, 1, 7, 4. That's correctly stored. So there's nothing wrong there. But look at the weights. They will be shaped like this. Oops. This. Why is it laying down? Because now do we update the weight sometime? I don't think we do. Then why is it? If we flip this. Let's check this one out manually. Yeah, 2 columns. That can be done, but that's possible. This map is this math is correct, but as soon as we change it, it's not correct. So for instance, if we look at this one, this column, this one's laying down. It is of that. Well, it's not time. It's not product. I remember that there's a difference. This works if you do transpose, but this does not work if you do transpose. That's so I had to generate it differently then. Wait, oh, I see an error here. Yeah. This will be equal to 4 values like this, I think. Yeah. You have to what do I have to do here? I'm gonna have to figure out how to generate this one differently. But it seems to be able to predict stuff. We should be able to predict things. That makes some sense. Look here again. We know the first column first, row second. So first column, second column, blah blah, and then we transpose this. Works perfect. But if you do it for the first one with 2 columns, transpose that, it doesn't work. You have to think. Sorry about that. Where were I? Yeah, maybe we should generate differently when it's so small. As it is the output layer. We can try that. Hidden layer is not 5. So we can't do that. Okay, well let's do this then. If neurons is equal to 1, else unclear. I'm gonna flip these. And I guess we're also going to flatten. Or wait, flatten there. Yeah, but that worked. Maybe potential just Oops. Yeah, no neural sets. Makes sense, but it should work. Yeah. So let's go with this for now. See that count multiply sequence by non-int of type float. It's a type error again. Self weights. Now we have this one. Count multiply sequence by non-int type float. Oh. Operands cannot work together with scopes 4 and 2. Interesting. So weight gradient we're trying to update the weight gradient. Update instead. That should be an integer. Input CO2, that's possible. Let's see where it messes up. We try to multiply by the inputs. What there would that be? Dot product. I think so. So let's hide these. Because the first one's fine. That one's okay. Oh, that one's okay. The output layer. This layer though, it's not. We have the inputs. They're correct. Self inputs. Wait. Right. Yeah, they're the same. And it's an array. Loss gradient is apparently a I'm gonna have to use dot product here. Also, the first here. Wait, we have inputs. It said. Should be no input dot product there. So we only have input stays a matrix. Loss gradient is not. Like it said. Also be fine. So hit 2 for self calculate set matrix. That's gradient. Well, let's print that one out too. Just double check it. Here we have it. Gradient layer 3. That is the second layer from the right. We have the self inputs. Okay, so calculate Z is suddenly a matrix. That makes sense. And the inputs. These aren't really the inputs anymore, are they? Are it was given some other inputs. Yeah, they were. They look here. They have 4 inputs each. It's like this. So something's off with the inputs. Where does the inputs? This be? Okay. Set inputs. Input gradient set. That input is wrong. So calculate set is being called here. Wait, what? Yeah, we call forward. And we call forward from here. Since this gets mixed up somehow. It loses some of the data. Let's put out the output inputs here. That's for both of them. Means we're gonna have to expand the inputs shape. So that's both of them. For instance, if we have so 4 neurons, 3 inputs. Wait, no. We're this works. But this one's only a so which means so inputs is the first one. What we're trying to do here now is this. Gonna have to add additional ones here, but maybe storing them isn't necessary. We can just compute them on the fly since we're gonna always gonna have to do once anyway. But maybe this go to this has the same dimensions amount of nodes. That's a problem. If we go to we define the shape, yes. No. Can wait. Save the input. Maybe we have to reduce some of the code. I think that might be a good idea. Gonna add the next layer attribute to each layer. So we'll add, set the names. Names. Is ever used again? this layer to the next layer. And if self, what? Move this here so you connect them both ways. So next layer. Wait, it would be previous layer. And no. Yeah, layer dot previous layer underscore. So we are looking back previously, and then self the layers. This one dot next layer. This layer. They're pointing to each other. Okay, that's good. Adding them to array then is kind of necessary. Let's remove that. Let's call this input layer. No. Actually, we add it. If self none sign. So I have taken the input layer. After adding it, I'll be able to predict stuff. So we want to type self.input layer forward inputs. And it's basically gonna turn stuff on the fly. Let's go to forward function. They all have their own forward function. If self.next layer not none, and forward it. Else, just return it. Okay. So calculate set. Calculate A. We're just gonna add these like this. So know that this will have a forward function. Know that this will have forward function. I know that this will not have one. Okay. We'll just pass it forward. That's cleaner, I think. I think it is definitely cleaner. So the layers will just pass everything between them. Let's see if that works. Here we have an error, of course. layers. That's fine. Where's the attribute? Ah. Let's the self dot layer mount build 0. You know what? Then here's. There we go. Oh, that doesn't exist. Okay. Can you add it? Maybe increment it afterwards? Maybe we can't. There we go. Layers. Why? Wait. Self dot layer is not. No, it's not. It's not. So what's this? Do this. Something else. Well, let's repeat layers. There's still layers being used here. Self dot layers. Damn it. What's I thinking? Okay. We can not connect this. So layers. Yeah, right. So just added a layer. And use. So empty. Last layer. Okay, what to do that? Last layer. Inner layer has no attribute shape. Set shape after. You forget to set the input shape. That's not great. Input shape is, let's see, after we added it, you dot set input shape. Let's make it input shape. I think that's great. Okay. Get the output shape. So we set the input shape to space. Well, four. Two. Gonna have columns first. Four inputs. Two. Inputs. And it waits. Hidden layer. That's right. I know. Okay, right. So it set the shape based on the output shape of the previous one. Select the number of neurons. Get output shape. None of these. And that will also be this shape. Right. previous layer, set the next layer of the previous layer. So connect the two layers. Poof. I'm gonna add one more. We need to know the input shape. And if we have, let's make some space here. I don't even know what this means anymore. Poof, poof. Okay. We have 1, 2, 3, 4, 1, 2. So these are neurons. They are connected. This. Oops. These will be we have two neurons here. The neurons will be X. Well, they will be because it will be 8 neurons. Right? Yeah. Okay. It not where it's the same as matrix. No, it's not. It is the same thing. And these will be flipped. Transposed. Those are the inputs. That's gonna be low. Okay. That means it set this input shape equal to the output shape. The output shape is this. So set input shape following. Apply. Tile. I think this will, or let's play around with that real quick. So we have 1, 2, 3, 4. Turn it to 2. That's not right. So just let's go in here for now. Then that, I guess. Self. Maybe. Okay, so we can create a model now. Let's explore if everything's properly connected. First layer weights. Get identity. Class layer. Why not? Model has no first layer. That's input layer. This should be output layer. No, it should not be. It should not. But it would be nice to maybe access it. But I guess it's unnecessary. Let's see. What I have here. I have the output shape. The output shape isn't really interesting, is it? I don't think so. But if you look at the input shape, that looks more correct. We should adjust this. Next layer. That could cause some errors. Yeah. Not all of them has an attribute. We can live without this. If it is the if instance is blah, blah, blah. It's not defined yet, so we can't do that. Maybe get identity should be in each layers. Perfect. Yeah. That's input shape. No, that is output layer. Perfect. Navigate them. Can we predict with it? Let's see. Can. Okay, so the predictions is working. What happens if you give multiple ones? That's not working. Predict one at a time. That's good enough. I'll be right back. See you in a minute. Okay, so I assume you can hear me again. I was just done reconnecting all the layers in a different way, and we can do predictions. Next step is fitting the model, so back propagations said, here we have an error. Dot product is t as inputs bias. So we pass its 10 values. All of the rows at the same time. Wait, what would do that? This. Check it out. Other weights. Well, that's not the point here. That's not good. So we're trying to predict multiple ones at the same time. Why we're doing that? Try to predict. Send all of them. Well, sure, we can have support for that, or we can just loop it. Or input and inputs. Res equals. Let's just call it array. Empty one. Res append. Self input layer. Forward. And then we just type array res as input instead, and parentheses, and well, that's something. My parent gives 4 values. That's not right. I think I did something wrong here under pred. Maybe not. I probably did. Look at the. We're gonna uncomment these. Maybe also. Oh, we could probably do with that. Might be a lot of shit comments here, but whatever. So wait, input. Yeah, real and pred. The predictor ones are, I think these are the attributes. Why do you get their attributes? Wait. This is not right. This is not right. There should be one integer. Oh, come on. Okay, so model does predict. You know what? Let's cheat here and type forward and add the core and just pass the inputs directly into the input layer. Here we see we get 4 values. We know that's wrong. We go to input layer, look at the predict there. Let's go forward. We look at the, sorry, not predict function, the forward function. And it will just return its next layer's forward result. And it should be a hidden layer. Hidden layer will calculate Z. Based on Z, it will upon the activation function. The activation function result will return until we reach the output layer. So the output layer will do the same thing, which is a mystery. Like, where does this turn into something else? So let's print self with name. No, self with get identity. Gonna add some formatting plus that. Okay. I should be able to follow how each A value changes. That would be seen here. Yeah, of course. So we go to the input layer here. It won't be A here, there will just be X. See, we start off with 4. Then we print out the result of the first ones are okay. So that's the output. It's strange. So we have the input shape here. Blah. This is wrong. This is not right. Change that. That's the output. And that, yeah, that is kind of correct. Yes. We also have the inlay 3, which we kind of skipped now. So that's the problem. We lose track of it. Let's go to hidden layer. Here we have it. So we have to call self next layer forward. Hey. And the has no attribute forward. So the output layer should have it forward. Wait, that's hidden. Output layer. There we go. I think I mixed those two together before. Let's call this again. 0, 0, so see that we can get values. That's good. If you look here though, we try to predict, get some error. Operands cannot broadcast together with shape 2, 4, 2, 0, or 1. So that's interesting. Because this one can take multiple inputs. There we go. This seems to be working. So that's great progress. Yeah. Bidding process, we know that's still not working. See, we get all these, blah blah, all the results here, but they're not that important anymore. So we're gonna hide some of the debugging. So the forwarding, count this out, and count that one out. We run all again. We should, yeah, pick the ones and all those. We should probably flatten the results. So the value we have predicted. They have the same dimension. There we go. Okay, so for layers in reverse, so we're gonna have to find the last layer. We have to store that, which we already do. Perfect. Hello, welcome to the chat. Big Valley Wiki. I'm not sure how to pronounce that. I'm sorry if I pronounce it wrong. Anyway, I hope you have a nice day, by the way. I surely am. Just enjoying this code challenge. So I was looking at backward propagation. Okay. Let's call it just Big Valley. Big Valley. Oh, Big Valley Wiki. Wait a minute. Okay, anyway. Are you having a good day, by the way? You have nice weather? Nice. Same here, but I haven't left the apartment the whole day. Yes to both. Cool. Yes, let's find this row. Okay. Let's see. So I've changed the structure of this neural network. So instead of keeping the layers just in an array, I've instead linked them together. Oh, a little hot in California. How hot is it in California right now? I bet if I were there now, I would like burn. It sound like a vampire. Okay, that's Fahrenheit. I have to convert that to the Celsius. Let's see, 102 F2C. Oh my god, that's warm. Fuck. Wow, that's like almost 1 degree Celsius from people start dying randomly. Yeah, I hope it's nice to live in California. I personally live in Stockholm, Sweden, so it's a bit different from where you live. 110. I almost feel sorry for you. My personal preference in Celsius is like 21. Let's see. Yeah, so like 70 Fahrenheit. That's what I prefer. Yeah, I guess get used to it after a while. Like lobsters in boiling water. If that's true, I don't know if that's true. It's never cold, never cold. I don't know if I would like that. I mean, it's nice with some cold weather sometimes. It's cozy. In the middle. Wait, how about... Wait, in California, do you guys get snow? I think you get some snow, right? Wait, never get cold. Okay, then you don't get snow at all, I guess. Wait, I have to check where California is exactly. Oh, crap. I moved that thing. Sorry about that. Blah, blah, blah. Oh, right. It's on the west coast. Wait, you get snow? Seriously? I have to bring it up on Google Maps. Oh, damn it. Oh, I can't imagine the guys down here getting snow at least. That must be... Wait, oh my god! That's Death Valley! Shit! And not sure about the other nature reserves. Well, national parks. Oh. Awesome. Well, anyway, I would cook on the street there. I would be like an egg. Ah, in the mountain northern parts. Yeah, that makes sense. That makes sense. If we talk about mountain northern parts, I mean, here in Sweden, we don't... some of those areas always have snow. No, like the... Ah, what do you say? The glaciers? You know, the ices? It's taller than most European countries. Like, you mean like taller? I mean by height or... Oh yeah, yeah, that's true. Maybe I should go back to Google Maps. Like, I'm curious. California. I'm sorry that I write in Swedish. Yeah, it is. Though this map isn't really correct to the scale, but yeah. Have you ever been to Europe? If you haven't been here, you should try visiting. Maybe it's expensive to travel here. Oh, you're Portuguese. But you live in California. So you... Wait, isn't Portugal next to Spain? Yeah. So, why did you all move from Portugal? Was it maybe a job opportunity? Oh, yeah, that makes sense. Oh, yeah, you don't want to get drafted. That's scary shit. Oh, someone else joined the chat. Hello. I wonder who it is. We're just talking about Portugal and California. It's what you usually do on a dev stream. So, let's see. Oh, colonial war. But where were the colonies that were at war? So, since they weren't... Wait, were they in Northern Africa? Maybe? Angola. Oh, where is Angola? I'm sorry, I have to cheat. Oh, Southern Africa. Ah, close enough. Huh. Oh. Damn. That looks warm. Oh, he was in the war. Did he survive? Horrible thing to ask, I'm sorry. But, no, I'm curious. Really hope he did. That's good. Glad to hear that. By the way, do you do any coding yourself? Since you're watching a development stream. Oh! Well, tell him I said hi then. And wish him well, of course. Oh, you do Python! Nice! What do you usually do with Python? Ah, nice. Game development is fun. We recently developed the game as a school project. We had like 1 month. It was super challenging since most of the team members were very new to programming. So basically, we were 8 people with 3 people who like knew how to code and solve coding problems. So we had to, while developing the game, also help the others learn how to code. But the end product was pretty cool, though never launched due to one person in the group apparently adding copyrighted material like sounds, music, images, and models. So like fuck, when it was time to like launch it, we couldn't. Bro, Pokemon is popular all over the world. Basically. When I started playing Pokemon, it was the first Pokemon I played was Pokemon Gold, then Pokemon Red, followed by Pokemon Blue, then Sapphire. After that, I actually stopped playing Pokemon and started spending more time playing World of Warcraft. Which one's your favorite, by the way? Not which Pokemon, of course. Which game? Oh, Ruby, yeah. Hey, you were a Ruby guy. Let's see, it was Ruby and Sapphire, right? And then they also added Emerald. Yeah. Cool. So, do you have like? Can I see the game somewhere? Any of the games you made? Thank you for following. So if you want, you could maybe drop a link in chat to the Git repository if it's public or something. Yeah, sure. Replit. I don't know what that is. Let me Google it. Oh, cool. Okay, so it's for you do a lot of things with it. Coding, you do the deployment, build share. Okay. Is it any good? Like, should I check it out sometime? The only tool I use right now for this, I'm not gonna deploy it anyway. There's nothing to deploy it, and I use Copilot. Wait, Streamlit? Have you used this before? Streamlit? I didn't know about it. see. I will open up here. Best one. Okay, I will start off up here. Can I run it somehow? Oh, okay. We don't have an account. Maybe I could create a free account. Just gonna do that on the other monitor. Give me a minute or two. GitHub. Okay, let's see. I got this work. I apparently have to verify my account first. Almost done. There we go. Okay. Do I have to fork it to run it? Python. Would be nice if they had forked it. Copy and paste it. Oh, you mean like there are no files? Oh, this is let's see. Called TMP1. Y. Wait, what? Oh. There we go. What's your name? I want to store banana. Sure. 1, 2, 3, 4, 5, 6, 7, 8. Enter first zip code. 5, 6, 7, 8. Aha, I have banana. Don't relock. Ah. So if I go into this file again, let's type apple. Oh. Password. 2, 3, 4. 4. Nice. Okay, what else did he do? Let's see. I want to see with this one. Gonna do it the same way. Same thing. Okay. Welcome to Furious Fighter. Choose your fighter. Okay. Murderous max damage. Furious. Whoa, I want to be Murderous max. Okay, you choose the Murderous max. Your opponent is Rebel Rook. What move will you use? Wait, what moves do I have? Wait, help me! Help me, Big Wally. What moves do I have? Oh! Oh no! It's in print? No, it didn't. Blah. Okay, I'm gonna use slap. Yes, you slapped. Your opponent slapped you. Oh, okay. I'm gonna use punch. Your opponent missed. Oh, you can miss. Cool. I missed the kick. Damn. No, it's fine. I can see them here in the code. You're healer. Okay, I can heal. Wait, I can strip. Armored up. Let's go with 7. And oh, damn, I need to. I skip the next turn. No. Will I win? I think I'm gonna win this. Yes! I won! Murderous... what's his name? Murderous Max won the battle. That's funny. It's a good job. Okay. I think I have to get back to the neural network, to be honest. Thank you so much for sharing the portfolio, by the way. Unless you had any specific ones you wanted me to look at. Like any of these. Oh. Any of these. There we go. Oh, is it also text-based, or is it with the graphics? But not really. Oh, okay. Another. Okay. So, what was I gonna say? We can, I can't figure out how to... Oh! Well, you could explore using a game engine. When we developed our game, we used Unity. So, I can show you some screenshots here. Like, Unity itself is not that hard to learn. And with that you use C, which is, yeah, exactly, C#. It's great to know. It's not that hard, really. It's a pretty good language. So, here's my portfolio. I'm just going to go to our projects. So, here, the game we made was a mobile VR horror game, basically. So you held your phone and looked around, and then you had joystick to move. So the idea was to go into a asylum where there were monsters. So the map inside the asylum was randomly generated, and the monsters spawned randomly, and your goal was to find the monsters and basically record them. But you also had to flee away from them when they were starting to hunt you, which was really fun to develop, though, as I said earlier, a bit tedious that so many in the group didn't have coding experience and didn't know how to solve coding challenges. Anyway, this game isn't available somewhere, unfortunately, because of the issue with the guy adding copyrighted content to it. So if you look here, for instance, but behind these achievements, there's an image that is stolen from Steam, I think, from a game there. That was pretty funny, because when he had added these pictures, we were like, whoa, how did you find these for free? And he didn't really tell us, because he didn't really understand English that well. And then at the end, when I double-checked with him, like, about the sources, he spilled the beans. He told us that. So probably he knew I was asking the first time, but he didn't want to admit it. Pygame or Python, right? I mean, by the name, it sounds like it. Pygame, open source Python. Yeah, it is. It does. Oh, it would be fun to build a platform like this. Super fun. Maybe I will check that out sometime. Maybe, but it is nice to also use a proper game engine. There's so many built-in tools. Yeah. So, I don't know if you're aware, but you use a game engine to, for instance, form the maps and also add a lot of the like basic physics and controls. But then to customize it, make the game yours, you have to write the code. Like, to make it more unique. Hold on, gotta charge my phone. There we go. Let's see. I don't remember what I was doing here. Right. Have you thought about taking an AI course or something? Oh, I haven't used Pygame, unfortunately, so I can't really help you there. But I get a feeling it has a huge community since it is Python based, and platformers are popular to make. But I'm very curious about the Unreal Engine. That would be very fun to try out. The graphics you can make there are just amazing. But when we did the game I showed you, the mobile horror game, I was working on a small weak laptop and it was burning up. It was suffering for a month. I'm pretty sure I should change the cooling paste on it, but I haven't. So it was, I don't know how warm it was running all days. I think, let's see, how warm does that computer usually run? I think it was around 80 degrees, like 8 hours a day for approximately a month. And this was like a just standard laptop for maybe 500 euros. Oh, the Chromebook, yeah, I feel you. That's probably worse. But hey, I mean, as long as you do basic things, it works. But then maybe if you're working on a Chromebook, I guess Unity isn't possible. Oh, by the way, someone joined us. Welcome to our chat about games. Maybe the second person in the stream now have also made games. It would be fun. All in the chat know some game development. I guess not. No reply. I guess it's just you and me, Big Wally. Oh no, when I say it like that, I think of Wally. Ah, so cute, robot. Right. So we have a crash here during the back propagation. Third, hidden layer 3. So friends cannot broadcast together. Shapes 4 and 2. We have the input of this shape. Okay. Well, tell me. I want to know. I love suggestions. I mean, it's just starting out, and the idea with this channel is mainly to just work on code and learn. That's the main goal. What? I think I found something weird. Oh, wait. Something weird from a Twitch channel. I can follow and unfollow over and... Wait. I can follow over and over. Make a million dogs. Million dogs. Wait, I can't see that. I think it only displays once for everyone else. I'm gonna try rerunning the animation for everyone. I mean, you can see that one, can you? Let me run it again. Can you see that? Okay, you can see that. But I couldn't see when you unfollowed and followed. I think that's just for you when you spam it. But I can see that you did it, like in my feed. Ah, no, no worries. Damn, people are starting to join in here. So, hello everyone. We have kind of had a break from the neural network development and been talking about programming overall, looking at some portfolios and talk about game development. So, if anyone here have an experience with Pygame, it would be very interesting to hear what you think about it. And if you don't know what Pygame is, it's apparently a free and open source Python program language library for games, obviously. I wonder. I can imagine that it's not too hard to use. Just out of curiosity, let's go to the wiki. Okay, Python T, people install the package, other info, installation, Mac installation. Well, I can't say that their wiki is any nice. So the stream delays or watch a video on it. Oh yeah, nice. I would love to have you around chat. Oh. Okay, let's close this down maybe and get back here. So I had some issues with the back propagation. So look, here we're trying to do an operation with two matrices that don't really match in size. This one, that's the input shape, which is this one. So let's draw some here. So the inputs, that is A. I'm gonna move this a bit. Like that. Okay. So we have, let's call it A1. Oh, you know what? These are actually this matrix is formed like this. It's vertical. So what might be confusing for you is that I'm using columns, then row in how I define things. So basically, if a matrix is of shape 2, 1, it is of the shape of this shape, x, x, like that, and not the other way around. Okay, so let's get back to this to see why we have this issue. We get this input. We have the weights. We have two weights. That's no. We don't have two weights, of course. Wait, are you? My laptop. I can watch the stream at the same time. It says my account doesn't exist. My Gmail. Oh wait. Where are you trying to make an account? Oh, trying to make an account for Pygame? Oh, that's odd. Wait, are you sure that you clicked on create account and not sign in? Oops. Double check that you pressed sign up or create account and not just signing with account you don't have. Because the error you got, account doesn't exist. I mean, that's an error you would get if you try to sign in, right? Okay, so that input, we have to calculate Z. Should be the third one, superscript 3. That would be Z1. We have Z2. Let's see. I went to register and then it's account. Exists now. And then say to go to confirm accounts. Maybe yeah, there are interpreters for Godot. I heard that too. Godot also has a big community apparently, but maybe they are meant for different types of games. I got the feeling that Pygame is made for platformers, while Godot can be used for anything basically. Maybe you also can re-request the activation link. Wait, it asked you to confirm the account, but did you receive an email or did you just... You should have received an email. Of course. Right? Oh, I see my problem here. So, we're gonna remove this. The reason why I'm getting the error here. Wait, I'm trying to do. What am I trying to do? Oh, how do I open the Godot file? I downloaded it. Well, how you open the Godot file? Does you said you have a Chromebook, didn't you? Can you run Godot on Chromebooks? Close some of these files. Man, I don't think you can Godot on a Chromebook. Wait, maybe you can. Oh, have you tried this? So apparently it works in Chromebook's Linux app mode. Give this a try. I'll send you the link. Maybe. Hopefully. That would be fun if you got it to work. Let's see. Where was I? Okay. So, give it a try and let me know if it works. And the other one who just joined the stream, welcome. I hope you have a nice day. I know we are. We've been talking about games and game engines for a while now. It's been a nice break from the neural network. So self-input, put array, multiply that by this array. So it has dot product. So if we have these two matrices. No, let's Oh, whoa. There we go. These two can't be multiplied with, well, you can't apply dot product on them. But if you extend the first one, like so, you suddenly can. So that's what we got to do. We will scroll up, look for what we'll look for. By the way, would you like me to add a add like a background to the chat in the stream? Maybe that would help you guys read it, because I feel like I hide it sometimes for you, and I feel bad when I do that. That's why I keep like this right now. We can shrink it. There we go. Then we have the plan. Oh, hiding it for you again. Okay, so the inputs needs to be adjusted. Yeah, I will put this one up here. At least you can see the latest messages. Okay. Oh crap! I gotta end the stream soon. By the way, because I'm gonna need dinner. It's almost 7 in the evening here, and I haven't had lunch since, I don't know, 4 hours ago. Not too bad. Nah, I don't need food. All I need is code, right? Oh, it doesn't work. I thought you were referring to me eating dinner. It doesn't work. I don't know. But did a Pygame have support for Chromebooks? Yeah. Okay, then go with that. Yes. It's probably better that you just try again. If it doesn't work, contact the support. I'm sure they will help. It's better that you get it to work, like get it to work properly. Since it is development, you want it to be stable. You want a stable environment. Let's say you were to get Godot to work with that half wonky solution, then there's great risk it might stop working one day, or just a patch or something. Okay, so you know that this layer has some problems with the input. We need to check the input shape of this one. We have it here. We could just shape. Okay, so we need to create a function that can change an input to fit that specific layer's input shape. Basically, what we want to do is this. We want to transform a subscript 2 to this. So we want to clone it, create multiple columns. think might be able to solve this for us. No. Okay, so return and p array. We're gonna type in input. Wait. Is it tilt? No. Tile. Yeah, okay. Self dot input shape, I guess. Instead of Final Fantasy, should I call first stream? Oh, I mean, first stream, why not? That's a pretty good name. I like that. If I saw that like a news article about the game, I would definitely get interested. It sounds first stream sounds cooler than like Need for Speed or just Call of Duty. First stream sounds really like the fantasy theme. And also, yeah, right, about this AI. So this AI isn't supposed to do anything specific. I'm just trying to build a like model that can that I can play around with. So the first challenge is to build it to be a basic neural network that can be trained on CSV files. In this case, it will predict how much power that's being generated based on 4 attributes. So it's very simple, but the plan is to extend it to also be able to classify, for instance, digits and handwritten letters, you know. Oh, you can do Pippins or Pygame. Yeah, that makes sense. They said that on their wiki, I think. Right. So convert input to input shape. Then this naming is horrible. Maybe convert inputs. Okay, we're gonna have to find the correct layer and try this out. See if it works. So we want this layer. Well, let's be lazy. We can type model dot last layer dot previous layer. So go to the last layer. There's the output layer. Then go to the before that. I think that's where we have the issue. Output layer. I think, yeah. Okay, so dot and convert input. So this should give us this. Hold on, I will show you the desired output. That's a goal. If get that, I don't know. We'll see. Come on. Oh, god damn it. Wait. Convert input. Did I just... Oh, I have to run all the cells to redefine that class. Yeah, that's not right. Did you get Pygame to work, by the way? Yeah, the time difference is crazy. I know. Congratulations. I hope you managed to build some cool games with it. Let me know when you have built something I can look at. Okay, let's see if it can be interpreted as integer. What? that supposed to be an integer? Maybe it is. 1, 2. I'm gonna copy this. See what the input shape should look like. That one, 4, 4. What type of shape? Wait, that's just a array. What did I do? I'm gonna try to build my own engine. Oh wow! Yeah, I mean, you should definitely try to build your own engine. I think that's a great way to learn. Go for it. So anyway, I think I'm gonna have to end this stream now, unfortunately. Because I need to cook some dinner. I'm starving. Oh crap! Sorry. Oh yeah, object-oriented program is very useful when you need it. Otherwise, when you don't need it, it's a pain in the ass. I took a algorithms course where we were expected to use Java, and Java is object-oriented, and we were trying to use it in a way where you just code it around the objects all the time, and it was a nightmare. So much just boilerplate code. But anyway, man, thank you so much for staying in the chat so long. I hope I'll see you in a future stream, and good luck with the coding. Have a nice day, and hope to see some gaming develop soon. See ya.